Okay, so for those classes that didn't get to finish the last example of our notes today, here's how, excuse me, here's the rest of your notes. Please make sure you take them. All right, so then the last examples that we're working on, you're sketching graphs of these factored polynomials, and I'm wanting you to give me all of the values or intervals. We could also call those intervals, where f of x is greater than 0 or f of x is less than 0, excuse me. Okay, so we'll look at this first graph or this first polynomial right here that's in its factored form. And so we don't have to think very much about what its zeros are. We can see that x is equal to -2. That's a 0 for that one here. This one is x is equal to 3, and this one is x is equal to 4. And then -1/6 is always just -1/6. So we'll use the sign diagram, and we'll just take our factored forms, all of our factors, and we'll stack them on a sign diagram and draw our x-axis, and then we'll plot our zeros. So we have one at -2, one at 3, and one at 4. And so, excuse my notepad's not working very well today. I just can't seem to line things up. Okay, so this is our 0 for x plus 2, our 0 for x minus 3 is 3, and our 0 for x minus 4 is 4. Okay, so we're going to see what kind of outputs we get when we have these factors here. So -1/6 is always negative. So we're going to multiply all of these numbers times negative all the time. We'll mark that as negative. To the left of the 0, if I were to plug in a -3, -3 plus 2 is negative. So that means to the right of 0 we get positives. Same thing for x minus 3. 3 is the 0, so if I plug in a 0, 0 minus 3 is negative. So to the left is negative, to the right is positive. And then on x minus 4, to the left of 4 is 0, and to the right of 4 is positive. I'm sorry, to the left of 4 is negative, to the right of 4 is positive. So here's what we're going to do. We're going to take all of these outputs and multiply these factors. Negative times negative times negative times negative. That's going to produce a positive interval. Negative times positive times negative times negative produces a negative interval. Negative times positive times positive times negative is positive. And negative times positive times positive times positive is negative. Okay, so we're going to be sketching this graph. One other thing I will like you to find, though, is your y-intercept, because you can find your y-intercept so quickly. We're going to find our y-intercept by plugging in 0 for x. So we're doing -1/6 times 0 plus 2 times 0 minus 3 times 0 minus 4. So our f of 0, or our x-intercept, is -1/6 times 2 times -3 times -4. So I believe that's negative times negative times negative is going to produce a negative. And let's see, I'm going to multiply backwards. 12 times 2 is 24, and 1/6 of 24 is 4. So our y-intercept is 0, -4. Okay, so now we're going to sketch our graph using our critical points, our zeros, our y-intercept, and when we're above and below the graph. Okay, so I'm just going to scooch this down a little bit so I can draw a graph. Okay, there's our y-axis. Here's our x-axis. We know we're going to be coming down here to -4, so I'll put a point there. I'll put a point here at -2. There's a 0. We have a 0 at 3 and a 0 at 4. Okay, so let's take a look at what our graph is telling us to do. It's saying to the left of 2, we need to be positive, so we're going to be above. Between -2 and 3 on our x-axis, we're going to be below. Between 3 and 4, we're going to be above. And after 4, we're going to be below. So our graph is going to follow kind of this pattern here. Let me do that again. So above, below, positive is above, and then negative is below. So we'll just sketch a graph It doesn't have to be perfect, but it is a polynomial, so it does have to be curved. And notice that I really don't have much of a scale going on my y-axis. It's my x and my y. So that is an acceptable version or sketch of this polynomial. And we did have to identify when our f of x, or when our y's, were greater than 0. And that happened in the intervals from -infinity to -2, because we were definitely up in positive y's. And we were also in positive y's here in this little tiny section between 3 and 4. And you also had to note when your f of x or your y's were below 0. And those were the intervals between here. You had some negative results here and here. So between -2 and 3, and from 4 to infinity. And so that's an example of using the sign chart, your y-intercept if you can find it. Well, of course you can find it, and your zeros to sketch a graph. Not draw the perfect one, just sketch one. So let's do this next one. All right, so here we have another polynomial that's factored out. It's in its factored form, but do note that you do have some quantities or some factors that are being squared. So just remember that when you have a quantity being squared, it's always going to produce positive or zeros. It will not produce a negative. -5 squared is positive 25. So just remember that. So we're going to find all our zeros. So x squared equals 0. Square root both of those. X equals 0. So there's a 0. Here x's 0 is -2. This 0 is 1. And this 0 is 2. So when we go to construct our table or our sign diagram, we're going to be plotting the 0 at -2, the 0 at 1, and at 2. And so we'll take all of our factors here, our linear factors and our quadratic factors, x squared, x plus 2, x minus 1 quantity squared, and x minus 2, and we're going to plot those zeros. We're going to plot where do these factors produce positive outputs and negative outputs. So we'll draw our little graph there. All right, so x squared 0 is 0. X plus 2 0 is -2. X minus 1 0 is here, and x minus 2 0 is here. Okay, remembering that x squared, quantities squared, always produce positives or zeros. So all sections of the x-axis produce positives except for 0. X plus 2 to the left will produce a negative. To the left of it, 0 produces a negative, and to the right produces a positive. Here we have another quantity squared, which always produces a positive except for at 0. 0 squared is 0. And then we have x minus 2. So to the left of that 0 would be negative, and to the right of that 0 would be positive. So now let's see what our factor products will be. We have positive times negative times positive times negative, which is going to give us a positive product. So we'll be above the x-axis, below, 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 and above. Okay, so let's go ahead and see if we can find our y-intercept real quick. I'll put it over here. So our y-intercept is just when, I think it's right here at 0, because it's a function, so it only has y-intercept, one y-intercept, but let's go ahead and test it. The f of 0 is equal to 0 squared times all of this other stuff, whatever. That doesn't even matter because 0 times everything is 0. So definitely your y-intercept is at 0, 0. Little math logic there. So let's go ahead and graph our graph. And let's see. There's our y-axis. Here's our x-axis. And we have a 0 at -2, 1, 2, etc. So we'll plot those zeros at -2, 0, 1, and 2. Sorry about that big dot there. It's on the line, I promise. Okay, so here's what we know looking at our graph. If I come back up here and just kind of sketch what's happening, I'm starting above, I hit my 0, and I come down below, and then I have to come back up to my 0, and then I have to go back below, come back up to my 0, then I have to go back below, come up to my 0, and then I can go up again. So my graph's kind of following that idea right there. Let me see if I can get something good going here. So let's see. It's probably coming down, hitting some low. Oh, nope, that's not going to work. Let's try that again. Because it's got a curve, so it can't curve, curve, curve. It's doing something like that. We don't know how deep the dips are. Of course, we can find some intermediate values there to produce that, but I'm not asking for that right now. You'll notice that I didn't put a scale on my y-axis. So this could be a fairly accurate graph. Of course, you could test it on Desmos to see how you do. But there it is. Let's give our intervals of positive intervals and our negative intervals, or where our outputs are positive or negative, excuse me. Okay, so our f of x, or our y's, are positive between the intervals negative infinity and negative 2, and from 2 to infinity, based upon these outputs what we have up here. And then our f of x, or our y's, are less than 0 in the intervals in between, but not including the zeros. So negative 2 to 0, union 0 to 1, union 1 to 2. So that should help with your homework. And then the rest of the video, for those of you who missed class today, will happen after this part of the video. So continue to watch if you haven't seen any of today's notes. All right, so your important terms we're going to get started on today are the polynomial, which this is not going to be your first try at polynomials. You're in pre-calculus, for crying out loud. The intermediate value theorem and the sign diagram. So let's start with the definition of polynomial. Really important key term here, super important key term, is this right here, continuous. A polynomial is continuous, meaning it doesn't have a break in it. When you draw it on a graph, it's just this continuous smooth curves going throughout the whole coordinate plane. So no breaks, continuous, really important. In calculus, you're always trying to prove things, and you can only prove things when your graphs are continuous. So that's important, okay? Also, they're in a single variable, so they'll only have x's or only a's or whatever, containing one to many polynomial terms, poly means many, raised to positive integer powers. Graphs will be curves, period, unless it's constant or linear. So let's do a couple of examples over here, depictions. So a polynomial, sometimes they'll be notated the p of x, capital P of x, interestingly. Sometimes some textbooks will do a lowercase. I'm always used to seeing uppercase. Okay, so P of x is equal to, so let's see, all x's evidently, because I've said x, so the P of x is, let's say, 3x to the you pick, fifth, all right, plus 2x to the fourth minus 7x. This is a polynomial. How do I know? All of the variables are x. It's got 3 terms, so what kind of polynomial is it if it's got 3 terms? Trinomial, right? And all of my exponents are whole numbers, integers, and they're positive. Okay, so that's one. Here's another example. The f of a is equal to negative 5a. This is a polynomial. Is it a curved polynomial? Or is it linear? It's linear. Okay, or you could have the q of x equals x to the 5th plus x to the 4th plus x cubed plus x squared plus x plus 1. Okay, you'll see that one on the test. Guaranteed that polynomial is going to appear. It might appear in your homework, might appear in your notes. So that's a polynomial, and it has 5 terms, so you just call it a polynomial. And it's to the 5th degree because the largest exponent is a 5. So those are polynomials. Let's talk a little bit about what is not a polynomial, just so that we can really clear this up. not a poly. Okay, so if you see this, the f of x is equal to 1 over x. Why isn't that a polynomial? It has a break in it. You know it has a break in it. So that's one thing. But if I were to write this with an exponent, it would look like this. The f of x is equal to x to the negative 1 power. That's what that would look like. That's a negative integer. That's not a polynomial. Another one would be f of x is equal to the square root of x. Why isn't that a polynomial? What's that exponent if I put it in exponential form? X to the what power? X to the half power. That's a rational exponent. That does not create a polynomial. It's not a continuous curve. You know that that only goes in one direction forever, not in both directions forever. Okay, so that's not a polynomial. One other one would be this. Here's one more example, the absolute value of x. That doesn't graph curves, right? That graphs a v. So those are not polys. Here are polys. Okay, moving on to the intermediate value theorem, which you will be using quite a bit over these next couple days. The intermediate value theorem says this. First of all, let's define intermediate. Intermediate means between. That's what it means. Between values. And what's a theorem in math? A theorem is a law. It's been proven over and over and over and over and over again, and it has never been disproven. Therefore, we call it a theorem or a law. So it says this formal definition, if a function is a polyfunction, so that's a condition. It says if. If it's a polyfunction, that means it's continuous, yes? And the f of a, so the output of a does not equal the output of b, for a is less than b, then the function takes on every value between intermediate values, between this y and this y in the interval a from a to b. So I wrote that out in coordinate pairs so that you could kind of see what I'm talking about when I'm talking about f of a, f of b, talking about the y's. When I'm talking about a and b's, talking about the x's. So we'll come over here and we'll just do a couple little pictures quickly. So this is going to be my y-axis. This is going to be my x-axis. And I'm going to follow the rules. So there's a has to be less than b according to our if statement. And it's a polynomial. And my f of a cannot equal my f of b. So I'll put my f of a down here and my f of b up here. So I'm going to graph those two coordinates. Pairs. There they are. Now this is a poly function, so I should connect them with curves. Yes? Yes? Okay. And it's also continuous because it's a polynomial. So it could do something like, say, go like this and then like that. So it could do something like that. Now we don't know. It could go up and down a couple times. It could really cruise and do a lot of things. But here's what we're concerned about. The intermediate value theorem says that in between a and b, we're going to pick up all of these values right here of y, all of them. So this green line here is basically saying in between a and b, I'm going to pick up all the values between the f of a and the f of b, all of those y's. And what we're going to be looking for today is that we're going to be using the intermediate value theorem to try and prove that there's at least one zero between a and b. Is there a zero between a and b here? Yeah, it's right there. So if we get a negative output, say for example, a gives us a negative output, right? B gives us a positive output. If this is continuous, can my graph break and skip over the zero? No. And isn't zero always between negative and positive? So we'll be using the intermediate value theorem to try and prove that there's a zero between two x's. Okay? So it could look like that. It could also look like this. We'll do one more quick picture. Here's an x and here's a y axis. And again, we'll put a here and we'll put b here. But let's go ahead and put the f of a up here and the f of b down here. Okay, and we'll graph our f of a and our f of b. I'm not sure why I put that b up so high, but there it is. Okay, and it is poly function, so it's a curve, and it's continuous, so maybe it goes like that. We don't know. Again, it could go down and up a number of times, depending on how complicated the function is. But we're going to pick up all of these values right here. All of these y's in between f of a and f of b. So is there a 0 in between this a and b? Right there, there's a 0. So we will be using the intermediate value theorem to prove there's a 0 or not. Okay, all right, last one, sign diagram. This is the last one for today, the sign diagram. We'll be using it often because you're graphing in this unit, you're graphing a lot of polynomials. And look, polynomials are hard to graph perfectly. I'm just looking for sketches. I just want the critical points. Where are the zeros? Where's the y-intercept? When's the graph above the x-axis? When's the graph below the x-axis? That's all I care about. And make sure that you're course graphing curves and not like cusps or other weird little figures. Okay, so what's a sign diagram? Basically, we've used them many times. Compact tool, it's compact. It puts everything in one little table that we can look at. It's convenient, and it lets us see when we get negative results, when we get zeros, and when we get positives. If you haven't perfected it by now, if you're still in the intermediate level of sign diagrams, you need to become a master now. Here's the important point. In order to use a sign chart or a sign diagram, you have to factor that polynomial unless it's factored for you. So here's what I'm going to do. I'm going to give you a factored polynomial over here. Let's do x squared times x minus some number a times x plus some number c. You know what? Let's make this a b. Let's make it a b. Okay. So is this a polynomial? Remember, b and c are numbers. Okay. So is it a polynomial, all x's? Yeah, because b and c represent numbers. Okay. And are my exponents raised, are my x's raised to positive x integer powers? Right. This is x to the 4th if you multiply it out, if you expand it and then simplify. Okay, so it's already factored. Something to note that you could write down over here. When you have some quantity squared, some linear quantity squared where it's x, it's quadratic, but it's a perfect square. Squares always produce positives or zeros. If I square a -5, what's -5 times -5? 25. It doesn't matter what I square, I'll get a positive result unless I square 0. 0 squared 0. So when we go to make our sign diagram right now, let's identify our zeros. And then we'll make our sign diagram. What's the 0 for x squared? You know, x squared equals 0, so x equals 0. Okay, what's our 0 for x minus b? Positive b. That's right. What's our 0 for x minus x plus c? Negative c. That's right. You're just looking for the opposites all the time. All right. So we're going to make a little sign chart. We're going to make our x-axis down here. Remember, that's what this line is down here. Every time I create this, I'm just creating the x-axis. And I'm going to, first I'll plot the negative c because it's negative, and the 0, and the positive b. And I'll just stretch them out like that because I don't know what they represent, but they will give you a good indication of where things are plotted. And then we're going to take our factored forms over here and we're going to stack them. We're going to do 3 number lines. So x squared, x minus b, and x plus c. And we're going to see what kind of numbers do they produce in each interval. We have 4 intervals here. In each interval, what kind of numbers do they produce, positives or negatives? So 0 is our 0 for x squared. And since it's an x squared, it's either 0 or it's always positive, right? And x minus b, its 0 is over here at b. Now, since this x is a positive x, we know that to the left of 0, we get negative outputs. To the right of 0, we get positive outputs. And then x plus c 0 is negative c. And again, our x is positive here. So that means to the left we'll go negative and to the right we'll go positive. So these individual factors produce these outputs over these intervals. But what we have to do is we have to multiply them all together. So positive times negative is positive. So that's a positive interval from negative. So I'm going to say f of x is greater than 0 from negative infinity to negative c. We know that. Okay, let's go to the next one. Positive times positive is negative. All right, so f of x, my y's are going to be under, less than, clean that up, less than 0 over the interval negative c to 0. Okay, let's do the next one. What do we get? A negative. So also we get another negative output from 0 to b. And then in our last interval, we get a positive. So after b, we're going to be going above the graph or to positive results. So this is just a product table. We just multiply all these signs and figure out when we get positive products and negative products. Okay? All right, so we're moving on now. Questions? Okay, so we're switching to our note page now. If you're ready, here we go. I'll let you copy that down, your topics and your objectives, and then we will get started. Okay, so today's objective, polynomial graphs, just a little introduction and the intermediate value theorem. So we'll start off with sketching some cubic functions, or which are polynomials, and then we'll see where we go from there. So let's start with the parent function, of the cubic poly. So the parent function is f of x equals x cubed. So there's some things that I could ask you about that. I could say, where's its zeros? Where's its y-intercept? Etc. So let's find its 0. What's its 0? I just take the cubed root of both sides, and the cubed root of 0 is 0. Well, you know what? I think that's also my y-intercept then, right? Because that's the origin. Now, here's what I'm going to be asking you to do. On your graph, remember, I'm just asking you to sketch things, okay? So for your cubic functions here that are really not very complicated, they just have vertical stretches and shifts, I just need you to graph the 3 most crucial points. The 0, and then a number to the left of it and a number to the right of it. So let's go 1 to the right. What's 1 cubed? 1. What's negative 1 cubed? Negative 1. Okay, so remember this is a polynomial. So it's a curve and it's constant, it's continuous. So when you go to graph this, it is going to start off being a really steep curve. And then because it's a cube, what happens is as it gets close to the 0, it kind of flattens out. And then as it passes the 1s and the negative 1, it gets really steep again. And I'm not asking for perfection. I'm just asking for those critical points. That turning point right there at 0, 0. It's not really a turning point, but that's the 0. And then 1 to the left, 1 to the right. That's it. Got it? Okay, here we go. So for objective 1, you will be asked for, I think, 2 times on your homework. You might have to graph like 4 of them. But there's 2 problems where you're going to be sketching these cubic functions. And you'll be given values for your constant or your lead coefficient, C or A. So we're just sketch a graph. You don't have to write all the instructions, just write sketch a graph. Okay, so here we have A, which is the f of x is equal to 2x cubed minus some constant. And I am assigning the constant to be 3. Okay, so we're going to sketch the f of x is equal to 2x cubed minus 3. Okay, so if I were to write this in its transformational form, so I could see the horizontal and vertical shifts, it would look like this. 2 times x minus 0 quantity cubed minus 3. I bet those equal the same thing, right? So when you look at it in this form, you can see nothing horizontal action. No horizontal action. It's all vertical. So let's identify what this A is telling us to do. Vertically do what? Stretch times what? So we're going to do our Y because it's vertical. So we're going to change the Y times 2. And what is this 3 telling us? This minus 3. Yeah, it's down 3. So that's going to be Y minus 3. So that's all I'm really looking for here is just for you to practice graphing some cubics. Okay. So let's see, since we're shifting it down, I think I'll put my x-axis up a little bit higher. And I'm going to graph the parent function. Well, I'm going to graph the 3 critical points that we talked about, 0, 0, 1, 1, and negative 1, negative 1. I'm not going to graph them. I'm just going to plot them. And then I'm going to switch colors so that I can graph my f of x with my shifts. So let's start at our 0. Because it's the easiest one to do shifting with. We're going to multiply it by 2. 0 times 2 minus 3. So it's going to come down here. Okay, so now I've replotted my 0. It's down here on my y-intercept because you know that's my y-intercept. Negative 3. All right, now let's take this point right here where y equals 1 and let's stretch it vertically times 2. 2, and then shift it down 3. 1, 2, 3. Here I am at negative 1. But you can see the stretch, right? It's not up 1, right 1. Now it's up 2, right 1. Let's do this one. Multiply it. Negative 1 times 2. Negative 2. Shift it down 3. Where am I? Negative 5. Okay, remember to flatten it out through the 0. And then that wasn't very good. Let me do that again. Flatten it out. There we go. And then just label it f of x, and there you go. You have graphed it. Just a reminder of using your transformations whenever it's useful. Okay? Questions before we move on? Okay, we have 15 minutes. Let's see what we can do. Here we have the f of x is equal to ax cubed plus 2, where a, our lead coefficient, is negative 1/3. So we're going to do the f of x is equal to negative 1/3 x cubed plus 2. So let's take a look at our negative 1/3. Again, I could write this in transformational form. X minus 0 cubed plus 2. You can see it. No horizontal action. It's all vertical. There's no extra x's, nothing. Okay, so what is this telling us to do? That's not a stretch. Yeah, it's a compression. And it's also a flip, isn't it? Vertical reflection. So this is going to be a flip and compress. That's vertical. So we're going to do y times negative 1/3. And let's do them at the same time if you don't mind. Are you okay with that? Yeah. All right. And then this is telling us to do what? Up 2 vertically. Push it up 2. So we're going to do y plus 2. Actually, we're going to do negative 1/3 y plus 2. But we'll just do them one at a time. Okay. So drawing the graph. Now, since I'm shifting up, do you think I should put my x-axis down lower? Yeah, me too. All right. I'm also going, that's an x. I'm also going to plan, because I'm multiplying by 1/3. When I go to put my marks in for 1 and 2 and 3 like that, I'm going to go in and put like thirds in between them, because I'm definitely going to be compressing them a bit. Okay, and I'll do my parent function here, here, and here. Just the points. And then I'm going to pick up my red pen, and I'm going to do my compressions and shifts. So we're going to take our 0, multiply it by negative 1/3, which is still 0, and then up 2. So there's that one. Let's take this negative 1. Negative 1 times 1, negative 1/3. Positive 1/3. 1/3 plus 2 is 2 and 1/3. Okay, so there's that point. Look, it's definitely closer. It's up 1/3 and left. So that means we're going down 1/3 and right. You know that's what that means, right? So let's do 1. Y is 1. 1 times the negative 1/3 is negative 1/3 up to, that's up to 2/3 and up to 1 2/3. So it's there. That point should be closer to that. So it's going to go down, flatten out definitely, and then down. And there's your f of x. And there you go. Okay. So there's some practice with some cubic functions. You'll have to do that for homework. My suggestion is to use your transformations off the parent function. Okay. Now, really crucial, one of these questions is on the test. Like actually this question. I'm not telling you which one. Okay, number 2. Use the intermediate value theorem to show that the function has a 0 between a and b. So remember, a is your input, b is your input. So let's take a look at them. If to use IVT, it has to be continuous and a polynomial. Is this a continuous polynomial? This function. Does it fit the definition of a polynomial? Yes, so therefore it's continuous polynomial. We can use the intermediate value theorem. Is our a less than our b? Because that's part of our definition as well. Okay, then here's what we're going to do. We're going to do the f of a, which is 3 cubed minus 4 times 3 squared plus 3 times 3 minus 2. And today I'm just going to go ahead and do that math for you. The f of 3, that's supposed to say the f of 3, by the way. Sorry, the f of 3. Clean that up. So the f of 3 is negative 2. So notice I got a negative output. So if I'm using an intermediate value and I'm trying to find a 0 between a and b, what does b's output have to be? If my 3 is negative, then my 4 has to be, in order for there to be a 0 between them. Well, let's see. So let's do the f of 4. So that would be 4 cubed minus 4 times 4 squared, which is also 4 cubed, right? 4 times, that's 4 to the first? Yeah, so those just cancel each other out, so that's nice. Plus 3 times 4, which is 12, minus 2. So the f of 4 is what? 10. Ooh, that's positive. So what does that tell you? There's a 0 between them. We could graph them. Here's 3, here's 4. 3, negative 2, and 4, 10. If this is a polynomial and it's continuous, does it have a 0 somewhere? At least one? Because you know it could go like this a couple times. It could. Did you know? It could. But we know there's at least one. Don't do that funky little line that I just did. That's just a demonstration. So here's what you have to say. First, you have to say that f is a continuous poly. You have to say that because that's the condition for the intermediate value theorem. Therefore, there is a 0 between 3 and 4. And you could be really picky because 3 produced a negative and 4 produced a positive, and there must be a 0 between them. But that's acceptable for me. Okay? All right, next one. So here we have another one. Is it continuous? Is it a poly? Yeah? Yep, all our exponents are positive whole numbers. There we go. So, and it's continuous because it's polynomial. So we're going to do the f of half, which is half to the 5th plus half to the 3rd plus half squared plus half plus 1. And I'll do the math for you this time. The f of half. P.S. I am rising positive numbers to positive exponents, so you know what all these numbers equal when I add them together? A bunch of positives. Positive, 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 positive. So my answer is definitely positive, and it is positive 61 over 32. And the f of 1. I'm thinking I'm just about to take 1 and raise it to a bunch of numbers. What difference does that make? What's 1 to the 100th power? 1 times 1 times 1 times 1 forever, right? So what's my sum? 1. Oh, 5. Yeah, it's 5. Hello, 1. I'm all being all smarty pants. 5. They're both positive. Wait a second. Can I verify there's a 0 between these two numbers if they're both positive? Will the intermediate value theorem help me determine a 0? If I were to graph it, here's 1/2, and here's 1, and 1/2 is giving me 2 point something, and 1 is giving me 5. Can I guarantee there's a 0 between them? No. Okay, so f is continuous. However, we can't verify there is a 0 between 1/2 and 1 by IVT. IVT does not help us to do that. We'd get out a calculator or factor or something. Okay? One of those questions is on the test. What? Huh? Somebody told you?
No, you just said it right now.
I said one of them.
I know, when we were doing the other thing, the terms, you're like...
Oh, yeah, I did say that. You are a smart cookie. Okay, number 3. Okay, it says, and we kind of did this already when we did your vocabulary terms. This part, the f of x is greater than and f of x is less than. But we're also going to sketch a graph. Remember this, polynomials are hard to graph. I'm not looking for perfection. I'm looking for the critical points, the zeros, the y-intercepts, when the graph goes above, when the graph goes below. Right, I can stop the video now.